IBM Cloud is a vehicle that allows for innovation. That is realized in many ways using traditional computing resources, but it also opens up access to truly breakthrough technologies, such as IBM's recently announced 20-qubit quantum computer, which is hosted in our Yorktown research facility. So what is quantum computing and why should we care? Let's stand back for a second and consider the incredible growth and explosion of capability that we've all witnessed in our lives involving computing. About 100 years ago now, the earliest digital computers were created using mechanical devices. They took up huge rooms of racks and racks of equipment, requiring incredible amounts of electrical power and a very expensive infrastructure to run. So they were only used initially in research and government kinds of settings. However, engineers were very rapidly able to change the underlying technology that supported the computers to various electrical mechanical devices. They introduced a vacuum tube, and then eventually with the invention of the transistor, they were able to begin a very rapid journey of miniaturization of this technology, which also represented or resulted in the ability to greatly reduce the processing power of these computers. In today's world, we're surrounded by these things and we may or may not even realize it. There are the obvious computers such as laptops and desktop computers that we've most all used, but it also powers our smartphones, our pad devices, and even more subtly is it embedded in devices such as our automobiles, our televisions, our appliances, including refrigerators, and other uses that you might not ever even think about. So digital computing has taken us quite a ways. However, in today's world, our scientists are creating even more expansive uses of computing and different models that will take us much further than the digital computing model will be able to. A quick review of some of that journey starts with a gentleman named Claude Shannon, who in the mid-20th century taught us to think of information as bits, that is zeros and ones. This abstraction allowed us to leverage the rapid technology improvements at the physical level to support this digital computing. He is known as the father of information theory. Later on in the 1960s and 70s, two IBM fellows, Rolf Landauer and Charlie Bennett, stretched the theories of information and physics to expand our vision of computing possibilities. Charlie became one of the founders of quantum computation theory. Many of us are familiar with the underlying building block of digital computers, the bit, which represents either a 1 or a 0. Quantum computers build on a different building block called the qubit, which can represent 1, 0, or both of those numbers at the same time. This is possible by leveraging modern physics theories of quantum mechanics. There's a property called superposition, which is leveraged to allow a single qubit to hold a much larger set of states than the two allowed in a bit. So a bit can either be on or off, 0 or a 1, whereas a qubit can be 1, a 0, or a large variety of combinations of 1 and 0 at the same time. As the number of qubits grows, they can hold exponentially more numbers of states than the traditional collection of bits can. Another key quantum property in physics is called entanglement. You can think of this as correlations between the qubits, the individual qubits. And this allows for much more powerful algorithms to be applied to this technology to create more powerful processing speed available to us in our computers. To emphasize the differences, remember that classically, Each bit is either a 0 or a 1, giving it two and only two possible states. When you read an individual bit or a collection of bits, the bits don't change. This allows us to copy that information to other locations. And each bit is self-contained. Bit 1 it only depends on itself for its state of 0 or 1. It doesn't rely on bit 2 or 3 or any other external force to fully understand its value. Now let's look at qubits at a high level to contrast it. Qubits also have a definite state at any particular time, but again, because of superposition, it could be one of many more states than just the two that a bit is allowed to represent. Strangely, again, this is the weird modern physics, when you read a qubit, you can actually change its state simply by observing or reading it. So that makes it impossible to simply copy the data from a set of qubits like you can in today's world of normal bits. And finally, this meaning of information correlations can be used across the whole of a set of qubits. And essentially, you think of it as the whole is much more than a sum of its parts as compared to today's traditional computing model. There's been much written about the information theory behind bits and qubits, and it can get quite technical. Suffice it to say for now that these new computing building blocks enable us to develop computing systems that might address problems that are far beyond what's possible with today's digital computers, as powerful as they are. Many of these problems have significant value. Fields such as cryptography, modeling of natural objects such as molecules and advanced materials will both be advanced by the use of quantum computing because of the nature of the computations that we can use in those fields. There are some IT topics that are all the rage today, adding value to many organizations, including many businesses. Machine learning or artificial intelligence, and searching and leveraging big data, which is exploding today, are both key IT areas that also lend themselves to the kinds of computations that quantum computing will be able to offer. So you might imagine, as you look across these categories, and there are many others in science and business, that can be greatly expanded or enhanced by this new style of computing technology. IBM is building new quantum computing systems. Similar to how digital computers have been built up from transistors, IBM Research has successfully built advanced quantum computers out of qubits, which are now being used and deployed in scaled up in very large computing systems. These new systems have to be cooled to near 0 degrees Kelvin, or absolute zero. To get an idea of how cold that is, that's cooler than outer space. Here's a photograph of a small quantum computer using current technology. Much of this, again, is to control and maintain the electrical environment and the very cold physical surroundings that these new qubit building blocks require to be able to function. And it might remind you of the early days of the digital path that we described in the rooms of large computing equipment that was required in the initial days of that journey. IBM is making rapid progress in scaling up these technologies. In November 2017, IBM announced a working 50-qubit computer and is making 20-qubit-based systems available on the IBM Cloud. So unlike the early days of digital computers, you don't have to build a huge and very expensive laboratory to house your own machine. And you don't have to build all of the labor to support it and the very expensive electrical power supplies, etc. Because IBM is going to allow interested individuals and organizations to access this technology through the internet. And normal devices such as laptops, iPads, and even smartphones can be used to interface to this new technology by leveraging it through the IBM Cloud. IBM Q systems are the most advanced quantum computing systems, and IBM is going to make them available to qualified business and science users, again, via the IBM Cloud and hosted in IBM facilities. The place to get started is our website, the IBM Computing Experience. Here you'll find tutorials and access to tools such as a quantum computing simulator and graphical programming tools. There are also facilities to collaborate, including a user community and a library of technical papers written by scientists to date about the technology, the computational theory, and the uses of our technology up till this time. So there's quite a bit you can see at this site to get started. User guides step you through the concepts and details of actually using our technology, and the full software developer kit is available on the public GitHub repository, so you can download it to develop the code yourself on your device. Programming for this environment is done in a very graphical mannerism, and this is just a snapshot of the general appearance of that environment. What's maybe not obvious here is that there's an extensive library of capabilities or functions that you can build from. So you don't have to start from the very scratch and in the minimal building blocks. You can actually build on work that a lot of scientists have already done for you and create capabilities to use these computers for your own purposes. I hope you'll explore these resources to build your knowledge of quantum computing and to begin to leverage this new technology on the IBM Cloud. Our quantum computing landing page is a great place to stay current on IBM and the industry's developments in this broad field. The Quantum Experience website is the one we mentioned briefly and will help you actually get started using our technology and learning how to program on these computing systems. And finally, the IBM Research Frontiers site will keep you abreast of the broader leading-edge developments in the entire field of information technology. Thank you very much.